Welcome to the Deep Dive. We're here to help you understand the important shifts happening in AI. And today we're looking at something pretty significant, a challenge that could really change how AI develops. It's this looming data crunch. You might have seen some analyses suggesting that we could run out of high-quality human-generated data maybe as soon as 2028. Think about that. The very stuff fueling these massive language models, we might hit a limit in just a few years. It's potentially a major bottleneck. So our deep dive today is going to explore some really fascinating new research tackling this exact problem. We'll be comparing two main types of language models. You've got autoregressive models, AR models, which have been the standard for a long time. And then there are these diffusion models, a newer alternative that's showing a lot of promise.
Yeah, and this paper we're looking at, diffusion beats autoregressive in data-constrained settings. It has a core finding that's, well, pretty surprising. It basically shows that diffusion models can actually significantly outperform AR models, especially, and this is the key part, when the main limitation isn't computing power, but the amount of available data.
Right. So our mission for you, the listener, is to unpack why. What makes these diffusion models suddenly so good when data is scarce? Why do they seem to thrive where AR models struggle under those conditions? And, what does this mean for the future of AI, especially as we approach that potential data wall? Let's dig in.
Okay, so for a while now, the big AI breakthroughs, especially with large language models, have relied on scaling up. Throw more compute power at it, feed it more high-quality text, and the models get better. It seemed like a reliable formula. It did.
Yeah.
But there's a fundamental issue emerging now. Compute keeps getting cheaper, more available, but high-quality data, especially text written by humans, that's not growing nearly as fast. It's becoming stagnant, relatively speaking. The well is, you could say, starting to look a bit dry.
And the models that really benefited from that old scaling formula were mainly these autoregressive or AR models. Their core idea is pretty straightforward, right? They predict the next word or token based only on the words that came before it. It's strictly sequential, left to right, like writing a sentence one word after the next, always looking back.
Exactly, and that's where diffusion models offer a really different angle. Instead of that fixed left-to-right structure, they work differently. They model text using what's called a random order factorization. You can sort of picture it like this. They learn by taking a sentence, adding noise-blurring words out, maybe masking them, and then the model learns to remove that noise, to put the words back correctly. But critically, it can learn to do this reconstruction in, well, almost any order, not just left to right. This means they get trained on a much more diverse set of prediction tasks and orderings for the same piece of text, much more flexible than AR.
Okay, but for a long time, the general thinking, based on earlier studies, was that diffusion models were, frankly, computationally expensive. People thought they needed, maybe up to 16 times more compute than AR models to get similar results, at least when trained for just one pass over the data.
Right. And that perceived compute cost was a big hurdle. It definitely slowed down their adoption. But this brings us to the critical point of this new research, those older comparisons. They often mixed up compute efficiency with data efficiency. They mostly looked at single epoch training, seeing each piece of data just once. This new study, however, specifically looks at masked diffusion models in data-constrained settings. That means training involves multiple passes, or epochs, over the same limited data set.
So it's about what happens when you have to reuse your data because you don't have endless amounts of new stuff.
Precisely. And that's where the picture completely changes.
Okay, so what happens?
Well, the research finds that while AR models might start off better at lower compute levels, near that efficient chinchilla optimal point people talk about, they hit a ceiling pretty quickly when you keep feeding them the same data.
They saturate.
Yeah, they saturate. They stop improving much, and then they can actually start to overfit. It's like they just memorize the training examples instead of learning the underlying patterns.
Okay, but diffusion models.
Diffusion models, in contrast, just keep getting better with more compute, even with lots of data repetition. Remarkably, they showed no signs of overfitting within the study's budget, even after seeing the data many, many times. They ended up performing better overall.
So they're much better at extracting value from repeated data.
It seems so. They just keep finding useful signals where AR models plateau.
Is there a specific example from the paper that shows this?
Yes, figure 2 is quite telling. They tested this in a regime with only 100 million unique tokens, which sounds like a lot, but it's small for these models. The diffusion models kept improving and reached a final validation loss, basically a measure of error of 3.55. The best AR model, using the same data and similar compute budget over repeated epochs, stalled out at 3.71.
So lower is better for loss. That 3.55 versus 3.71, while it might seem small, it represents a much bigger improvement for diffusion, right?
It does. It showed diffusion models reduced their error by about 67% from the start, whereas AR models only managed about 48%. They just squeezed more learning out of each repeated token.
Okay, that ability to keep learning from the same data is obviously key. Did the study quantify how much better diffusion models are at this reuse?
They did. They use a parameter called RD, which you can think of it as representing the half-life of data reuse. Essentially, how many times can you repeat the data before the benefits start to drop off significantly?
And what did they find? Was there a big difference?
A huge difference. For AR models, this RD value was about 32, which means they see serious diminishing returns after only about, say, 4 epochs. 4 passes over the data. After that, repeating it doesn't help nearly as much.
Only 4 times.
Roughly, yes. But for the diffusion models, the RD was around 513.
Wow, 513 versus 32. That's a massive gap.
It is. It suggests diffusion models can potentially benefit from hundreds of passes over the same data, continuing to learn. Think of it like rereading a complex book. An AR model gets most of what it can after 4 reads. A diffusion model finds new insights even on the 100th read.
That's a great analogy.
And figure 5 in the paper illustrates this vividly. AR models get almost peak benefit around epoch 4. Beyond that, repeating data isn't much better than just stopping. Diffusion models, though, they showed benefits from repeating data for up to 100 epochs that were almost as good as if they'd been given fresh data each time.
Incredible robustness to data repetition then.
Definitely. They just keep learning where AR models hit that wall. So this naturally leads to a practical question. When should you choose one over the other? The research offers something called the critical compute point, or SICRIT.
The crit. Okay, what's that?
It's the threshold, the specific amount of computing power where, for a given amount of unique data, the fusion models start to beat AR model.
So it helps you decide based on your resources. If you have X amount of data, you need Y amount of compute before diffusion becomes the better bet.
You got it. And they even found a mathematical relationship for it, a power law.
Oh, useful. What's the formula?
SICRIT, the critical compute point for a certain amount of unique data, U scales with U raised to the power of about 2.174.
Okay, so secret U is proportional to U2.174. That gives practitioners a real tool, doesn't it? A way to estimate the crossover point based on their specific data constraints.
It does. It provides a quantitative guide for making that modeling choice. And importantly, these advantages weren't just theoretical, like looking only at the validation loss metric. They tested the best models from both types on actual downstream tasks, things like question answering, common sense reasoning. ARC-Easy, Boole, Q, Hellaswag, Lambada were some of them. The diffusion models consistently performed better on these practical benchmarks too, so the gains in data efficiency really translate into better real-world language understanding when data is limited.
Right, so it's not just an internal training metric improving, it actually makes the models better at tasks we care about.
That's what the results indicate.
Okay, this is fascinating.
Yeah.
We see that diffusion wins with repeated data, and that AR is more compute efficient initially. But why? What's the mechanism? The paper must have some ideas, right?
It does offer some compelling hypotheses. For diffusion's amazing data efficiency, the key idea is something they call implicit data augmentation.
Implicit data augmentation, what does that mean?
Remember how diffusion models learn by denoising, by predicting masked words in various random orders? Because they encounter so many different prediction tasks and orderings for the same sentence, unlike AR's fixed left to right, they effectively extract more signal, more information, from each example over repeated viewings. It's sort of like looking at an object from many different angles. Each view gives you a bit more information, leading to a richer, more robust understanding. This constant variation acts like a built-in data augmentation, helping the model generalize better, much like random cropping or rotation helps image models.
That makes a lot of sense. So each pass, even over the same data, offers a slightly new challenge, a new perspective, forcing the model to learn more deeply.
That seems to be the idea.
Okay, so then flip side. Why are AR models more compute efficient at the start? What gives them that initial speed advantage?
2 main reasons are proposed. First, order specialization. Because AR models only ever train on that fixed left-to-right prediction task, every single calculation, every gradient update reinforces that one specific skill.
They become specialists.
Highly specialized. Like an athlete training for only one event, they get very, very efficient at that specific task because it's all they practice.
Okay. And the second reason?
Stronger supervision per update. In AR training, every single token in the sequence provides a direct learning signal. The model predicts a word, compares it to the actual word, gets an error signal, very direct, very dense feedback. Diffusion models, on the other hand, usually only calculate the error on the subset of tokens that were masked or noised in that particular step. So even though the information flows through the whole model, the direct supervision signal per step is a bit sparser initially.
Got it. So AR gets more direct feedback per calculation early on, making it faster to learn that one specific task in a single pass. But diffusion's varied tasks, while initially slower, pay off hugely when data has to be reused.
That's the core trade-off highlighted by this research, yes.
This has really flipped some common assumptions on their head. It strongly suggests that the idea of AR models being universally better is, well, not quite right. It really seems the best choice depends critically on what your main limitation is.
I think that's the crucial takeaway for you, the listener. If you're working in AI, developing or training these models, the message is pretty clear. If your bottleneck is primarily compute, you have plenty of data but limited processing power, then autoregressive models are likely still your most efficient bet, especially initially. But if your main constraint is data, you have a limited finite data set you need to leverage as much as possible, then diffusion models present a really compelling and perhaps previously overlooked advantage.
They warrant serious consideration in that scenario.
Absolutely. And it's worth thinking, too, that these principles might extend beyond just language. Anywhere you have sequence modeling tasks, robotics, maybe healthcare data, genomics, where getting large amounts of high-quality data is difficult or expensive, these findings about diffusion models could be highly relevant.
That's a great point. So as we wrap up, maybe a final thought for you, the listener, to consider. As we face this potential plateau in high-quality data availability, maybe efficiently reusing the data we do have isn't just about optimization anymore. Perhaps mastering data efficiency, understanding how models like diffusion achieve it, is actually becoming the next major frontier for scaling AI. What new approaches might emerge when the focus shifts squarely onto getting the absolute most out of every single data point? Something to think about.